Hi, Mick McQuaid here with the second video for day 15 of iste780, Data-Driven Knowledge Discovery. And in this video I'd like to talk about bagging random forests and boosting. And these are very closely related techniques. Bagging and random forests, in fact, could be construed as one technique with just a slight change. So let's start here with bagging. So bagging stands for bootstrap aggregation. And the idea here is it would be nice, the general idea here is that if you take the average of a set of observations, you can reduce the variance. So if you have a set of observations with each one having variance sigma squared, the variance of the mean of those observations is going to be sigma squared over n. So taking that idea, it would be nice if what we would like to be able to do is to take many training sets, build a separate prediction model using each training set, and take the average of the resulting predictions. That would be really great if we had many training sets, but we don't, and that's where bootstrapping comes in. So what we're going to do instead is take bootstrap samples from the only training data set that we've got. And we're going to generate B different bootstrapped training sets, and then we're going to train our method on each bootstrap training set, and then we're going to average all the predictions that we get from the different resulting trees. And so we have one estimate, which is an average, and that's bagging. That's all there is to it. It's better for prediction than it gives impressive improvements over individual trees. As a matter of fact, let's take a look at an example here. There's a picture here that has some test error rates for here are some test error rates for bagging and for random forests. Bagging is the mustard-colored one here, and a single tree. It says here that a single classification tree has an error rate of 45.7%. So a single tree would be up here, and so even with a relatively small number of trees, we get a massive improvement in the test classification error using bagging. So it's a useful, highly useful technique for improving the prediction over individual classification trees. Now I said we take the average. That's for regression. If we want to do classification, we can't take the average of yes and no votes, of course. So what we can do is take a majority vote. So we can use the same the same idea with regression trees and the same idea with classification trees. Just varying whether we use an average or a majority vote. Now, as I say, there's the prediction is really good, but there is a problem. It is difficult to tell what predictor mattered. Oh, wait a minute. Let me just go back here. So here's another example where bagging is working out pretty well. So here, the dashed line here shows the error from a single classification tree. The black and green lines are estimates for bagging. Now, I should mention that we have two different estimates. So this is the test error estimate. This is called the out of bagging estimate. And this would eventually, if you did enough trees, this would eventually converge with the test estimate. The out of bagging estimate arises from the fact that bagged trees only use 2/3 of the observations, so it's totally legitimate to use the remaining 1/3 as a test set. And so we predict using the out of bagged estimates, and in this case they're smaller than the test error estimates, but that won't always be the case. And as I say, if it's large enough, the estimates will converge. Okay, but it's hard to know what role the individual predictors play. So one thing that we can do is create a variable importance measure. And the way that we do this is compute the mean, well, in this particular case, this was a classification example, so they computed the mean decrease in the Gini index. So every time that the data set was split on the basis of a predictor, the decrease in the Gini index was calculated for that split. And so we find that this predictor played the largest role by far by that measure. And then we would do the same thing except with RSS in the regression case instead of the Gini index or entropy. So how are random forests different from this? Random forests are different in the sense that they take into account the possibility that there is one predictor that is really strong. If there's a possibility that one predictor is really strong, then there will be correlation among all the trees. All the various trees will choose to include that one strong predictor in their models. So consequently, their variance is not going to be reduced as much as it could be if the trees were uncorrelated. So the alteration that a random forest makes is to take a random. This is the alteration is a random sample of M predictors is chosen as split candidates, and the split can only use one of those predictors, not any of the predictors. So this means that the strong predictor, if there is one, doesn't get used all the time. And so this means that the trees are uncorrelated. And the size of M is typically chosen to be an integer that's closest to the square root of P. That's the number of dimensions. So in this case, P was 13, so the integer that's closest to the square root of 13 was 4. So M was chosen to be 4 in the case of the heart data. So, and it says this may sound crazy, but this is the rationale is this idea that a strong predictor is dominating too much, and that we would like to, if our goal is to reduce variance, then we would like to reduce the influence of this strong predictor on the various trees. Now, boosting goes even farther than this. So boosting is a little bit different in the sense that boosting doesn't use the bootstrap. Instead, boosting develops trees sequentially. So each tree is grown using information from previously grown trees. That's quite different from bootstrapping the trees. See, with bootstrapping, there would be a random element each time, and we would be emphasizing that random element. So boosting instead does the following. Given the current model, we fit a decision tree to the residuals from the model. So that means that instead of using Y as the response, we're actually using the residuals as the response. So we have this new decision tree. We add that into the fitted function to update the residuals. And each tree can be quite small. Each tree can be a stump. Each tree may have a depth of only 1. In fact, frequently they have a depth of 1. That's not okay. And they have these tuning parameters. So the number of trees, and the number of trees can get to be too large. So there can be overfitting. So the trees can be too large, and the shrinkage parameter is going to influence the number of trees. So if the shrinkage parameter you might want to be small, but if you make it too small, then you need too many trees and you risk overfitting. So these two tuning parameters are sort of interrelated. Their values are in a sense dependent on each other. And as I mentioned, each tree can be really small. D controls the number of splits in each tree, so that's the number of branches in each tree is controlled by D. And D equals 1 can be just dandy. And there's an example given here where D equals 1 is actually exactly the same as d equals 2. They don't look the same if you just look at the picture, but if you look at the caption to the picture, it says the standard errors make none of these differences significant. Standard errors are around 0.02, and if you look, this one sort of levels off around 0.13. So 2 standard errors away from this would be 0.11. 2 standard errors away from this would be 0.12. So these heavily overlap. These lines heavily overlap, and you can't really say that the random forest is worse in any significant way than boosting is. But they're all clearly quite good. They all clearly drive the error down and then become stable somewhere in this vicinity. So these are 3 techniques that are highly worthwhile to improve trees. There isn't too much to say about them. I mean, they're relatively small tweaks, and the techniques are all ones that you've learned before. So tomorrow I look forward to just doing the labs with them and understanding them better. I think that's pretty much all that I want to say about these techniques. So thank you for your attention, and I look forward to the lab tomorrow.